Oh, sorry. All right. So I decided to focus on the second part of my work, which is using the sampling-based method to do Bayesian inference instead of talking the whole thing about the EnKF. And so we will focus on the MCMC. So today we talk about the Bayesian inference of spatially varying Manning coefficients in the coastal ocean setting using polynomial chaos-based MCMC. So in this study, we work with the shallow water model, which solved the depth integrated Navier-Stokes equations. And in this shallow water model, we have two governing equations, which is a continuity equation and momentum equation. And in the momentum equation, we have this case-slip coefficients, which describe the bottom stress or the resistance of the water column against the seabed. And inside this case-slip coefficient, we have this so-called Manning coefficient, which is n over there. And this Manning coefficient describes the seabed surface. So it's the empirically derived parameters, and it is depend on the surface characteristic. Either it can be rocky, it can be a reef, it can be vegetation, and in fact, it's quite spatially variable, and it cannot be measured directly. So this leads us to the inference problem. So basically, you guys are familiar with Bayesian inference. So basically, we have some field that we want to infer, and we resort to the Bayesian rule, where we have the posterior of M, which is the field, is proportional to some likelihood multiplied by the prior. So we usually sampling the posterior using the MCMC approach. And in sampling the likelihood is very expensive because for each likelihood we need to do one run of the model. And to speed things up, we can use the PC surrogate to solve this problem. All right, so just to give you the context or the idea of the framework that we will be working with. So I want to show you the work, the result of the work from 2017. It's already published. And in this case, we also infer the field of Manning coefficient, but it's controlled by only two constant, alpha and beta. So we have mx, which is the whole field of Manning, and we have m1, m2, m3, which is the, like a vector that controls the structure of the whole field. We call it the zonal approach. So we have one in one area, one Manning coefficient, and another area, another Manning coefficient. And the variability inside is controlled entirely using alpha and beta. So our inference problem becomes the inference of the alpha and beta only. And in this process, we also build the surrogate for the solution, which show in the top right corner. So we see the water elevation over time of the surrogate model and the ADCIRC, which is full model, and it fits quite well. And below, we show the posterior of alpha and beta, and in conclusion, we can infer alpha and beta very well. However, this study, we only limit our dimension of the infer parameter to only 2, and we want to expand this framework to the higher dimension, the more spatially varying Manning coefficient. So in this talk, we will start talking about the Gaussian process and how do we do Bayesian inversion in this Gaussian process setting. And then we will talk about the coordinate transformation where we account for the uncertainty in the covariance hyperparameter as well. And then we will talk about how to build the PC surrogate accounting for this change of coordinates. And then after that, we will show some results. So we assume that our field, Manning field, is a center Gaussian process, which can be described using the covariance model. And we then can use the proper orthogonal decomposition, or in the simpler term that I want to use is KL expansion. And if we decompose this C, X, X prime, which is the covariance, we will get of course, the eigenfunction and eigenvalues lambda k and psi k. Psi k is the eigenfunction. And we can express this field using KL decomposition. And we have the eta k, which is a Gaussian random variable, which describes or characterizes the whole field. So in practice, we need to truncate this series to the k term. And then our inference problem becomes the inference of the eta, which is the vector of this random variables, Gaussian random variables. And below there, I just want to show what the likelihood look like for the Gaussian process. So most of the time, people assume that the covariance is fixed. But in reality, it's quite uncertain because we don't have the full knowledge about the covariance matrix. So we can write this covariance matrix on covariance function in terms of the function of Q, where Q is some hyperparameters. And hyperparameter can be length scale and can be variance, for example. Then if we write it in this way, then we have the field, which is depend on the Q as well. So we also have the KL decomposition, which also depend on Q. And also eigenfunction and eigenvalues also depend on Q. Then we have the new Bayesian rules that we try to infer eta, which is the coordinates, and also Q, which is the hyperparameter. So this diagram, I just want to show you how we do this. So to sampling the posterior, we start from sampling the Q, which is the hyperparameters. From these hyperparameters, we will obtain the eigenmodes by composing the covariance. Then we sampling eta, the coordinates, and then we can build the field from this KL expansion. And then we can integrate this into the model. And then we use this to compute the likelihood, and then we get the posterior. The challenge in this is that we have to do many KL decomposition, and we also have to do many model runs. So to solve this, we use the method called the chain of coordinates, and use the PC surrogate together, combined, to speed up this process. So how do we do the coordinate transformation? And what is the reference basis in this case? So notice that psi k, Q, which is an eigenfunction that depends on Q, is a complete orthogonal sequence in L2 space. So it means that in this space, we can represent the Gaussian process with many bases. And we can actually build the reference basis that we can represent all this process in this reference basis, and we can reuse it. We don't need to change the basis every time we change Q. So, and with this basis, we can do change of coordinates back and forth between one basis and another basis. So we start by defining psi tilde k. We call it a scale eigenfunction, which is a product between, of course, the square roots of lambda k and psi k. And we put that into the KL expansion to simplify. And we know that we have some coordinate transformation between the reference and this basis. So we can write it in the parentheses. We have this infinite sum. And BKK is just some coordinate transformation coefficient between the reference and this and any basis. So, and BK can be computed using the projection. We use orthogonality, and we can compute this. And if we manipulate this term, we truncate it. Basically, we can write this in the matrix form, which is show. We have a remote or no? We have this pointer here. We can actually write this coordinate transformation in matrix form. We have the operator BQ that map any eta from any reference, any basis to the eta bar in the reference basis. So we can actually approximate any Gaussian process, MKQ, using M bar K, which is the approximation in reference basis. So what is the reference basis that we're choosing? There's two ways to go about this. One, we can pick one hyperparameter Q, and then we say that any covariance that built upon this Q will be our average reference covariance. Or we can just do the average over Q of the covariance, and then we get this Q average covariance function. And we choose this one because it's optimal in terms of the representation error over Q. Now, after we do this build coordinate transformation matrix and we build the reference basis, we also want to build a PC surrogate to speed up our likelihood sampling. But we want to make sure that this construction is consistent with the coordinate transformation we made before. So we have to also build the coordinate transformation matrix B tilde here for the PC expansion. And PC expansion is just the approximation of the full solution U eta Q using summation of the term of the coefficient multiplied by some polynomials. And this polynomial inside have the germ psi, which is a function of eta and Q. and it's expressed through the coordinate transformation b tilde eta, and there's some division with some square root of the lambda k, because we need to rescale it back to be consistent with the previous construction. Then, and in this work, you notice that b tilde kl is also depend on q, and to build this coordinate transformation matrix is really expensive too, because you need to do kl decomposition every time. So we also build the PC surrogate using the PC expansion of this coordinate transformation matrix as well. This is a lengthy subject, and I would just say that I used to calculate this PC coefficient to be used in the inference. I used the pseudo-spectral projection method and sparse grid to compute the PC coefficients. So to sum up the whole process in 3 lines, first we have some reference covariance function. Then we can build the coordinate transformation b tilde q, and we represent this using the reference Gaussian process. And then we can build the PC surrogate with the same coordinate transformation. And then we use all of this in the sampling of the likelihood here. Then we get the posterior of the eta, which is the coordinate and the hyperparameter q, without the need to include the hyperparameter in our surrogate. So actually, this method has some limitation. The first one is the crossing between the eigenmodes. This just means that for some q, when we decompose the covariance, there will be the crossing between the eigenvalues. I mean, the first mode and the second mode may become the same values. And the ordering that we used to impose before may not work. So we have to always do this reordering, and it's become a lot of work. Another limitation is the number of PC inputs. So basically, we cannot have very large eta. So basically, we can have like 10, because otherwise the construction of the PC surrogate will be expensive. This can also be improved by using sparse quadrature in the PC expansion. So now we move to some results. So in this work, we do our experiment on the advanced circulation model, which is the shallow water equation that's solved on the unstructured using the finite element. And it has been validated in many high-class studies. And our domain is, we are working with this here, we call it idealized inlet with aperture domain, where we have the open ocean, and we have some landlocked area, and then we allow the water to go through the inlet, and it's forced with some tidal force. And we have these red dots, which are the observation points that we take the observations. So we employ the observation simulation system experiment, or OSSE. So we generate the synthetic water elevation data. We extract it from ADCIRC run. And the Manning coefficient field that given this data, we call it the truth. And we attempt to recover this truth using, of course, using the COCKL expansion and PC MCMC. So this model is run for 5 days, and we of course, we use tidal force, and then we also perturb the observation using Gaussian noise. And also for the prior of the eta, which is the coordinates, we use a Gaussian prior. And for the Q, which in our case is only the length scale, the correlation length, we use the uniform prior, which is so it's Jeffrey prior. And the range of this length scale is from 1,000 to 4,000, and we also normalize it for the sake of convenience in the inference. So we normalize it to 0 to 1. So let's look at some reconstruction of the true Manning coefficient. So at the left side here, we have the true field of Manning. We generate this using the one realization of eta and q. And so we have, and then we reconstruction using the KL expansion, and then we get this field. And in the middle here, we reconstruction the field using reference basis plus the change of basis. And on the right-hand side, we also use the reference basis and chain of coordinates, but instead we use the PC version of the chain of coordinates. And we see that the PC version works really well and can really represent the true meaning. See here I show the water elevation between using the surrogate model and the full model, and it fits pretty well. I will speeding up. This one is not. Okay. So let's look at the infer posterior PDF. So this is the raw sampling. So we have the first three figures. We have the infer of the KL coordinates. And the fourth one is the infer of hyperparameter Q, which is the length scale. So we can see that for the first one, the inference learned a lot from the data. And for the second mode and the third mode, it's not learned so much. And the point that I want to show here, the most important one, is that we now be able to infer the hyperparameter Q that used to build the true pretty accurately. But this is not very informative in terms of comparing the infer problem, the infer result to the truth, because they live in different bases. So in order for me to compare this to the truth, I need to transform them to the reference basis, which is using this relation B tilde eta to psi. And then after we do this and we compare our distribution to the truth, we see that the map estimation recover the truth really well for all three coordinates. So another way to look if we are successfully infer our meaning or not is to look directly at the field itself. So this is the truth, and we try the one to infer with the case that the prior is a fixed hyperparameter, and of course because they only infer the coordinate in some subspace, so it cannot really recover the truth. And now we also have the recovering using the average covariance. It's performed better than the fixed hyperparameter case, but it's still far off. And then if we use the COC method to account for the uncertainty in Q and also infer Q as well, then we get something that's very close to the true meaning coefficient. And the error map of those three also tells us the same story. So in the fixed Q case, there's a large error inside this landlog area. And for the average covariance case, there's some large error in this bottom area. And if we use the COC method, then we found that most of the places in the domain have very low error. So just to conclude, we effectively treat the covariant hyperparameter using the chain of coordinates. We also build the generic construction of the surrogate model using the reference basis. And then we accelerate both coordinate transformation and likelihood sampling using PC and using the PC surrogate. We successfully apply this to the context of the coastal ocean modeling. It's still in the initial state, but right now we are sure that it's working in our context. So the future work, we can improve the robustness of this method by better ordering the eigenmodes. And or we can explore the alternative approach based on the change of measure. The idea is that we keep the reference basis, but instead of going through all this coordinate transformation thing, we can just look at the change in the prior of the hyperparameter directly and treat them. So, yep, with that I conclude my talk. Hope for some questions. Thank you.
Thank you very much, Dr. Siripatana.